In this video, I want to do a quick overview of aldehydes and ketones. This is your Year 13 A-level topic, and you can use this video as an overview after having studied the topic. And it's also a good one for recap, of course, and also for overview, in the sense that you're about to study the topic and you want to go over aldehydes and ketones. The main things I want to cover in this video will be how we form aldehydes, so oxidation of alcohols, how we form ketones, oxidation of secondary alcohols, and reduction reactions of aldehydes and ketones, and then looking at the nucleophilic addition mechanisms for the reactions of aldehydes and ketones with hydride ion and with cyanide ion as your nucleophiles. So the first thing to look at is, what do we mean by a carbonyl compound? So for example, I'm actually trying to get my highlighter, but I can't seem to get my highlighter. Anyway, carbonyl compound family is this one here, as you can see on here, this carbonyl group. This C double bond O is your carbonyl group. An aldehyde is where you have a hydrogen attached to the carbonyl. To the carbonyl carbon, I'm going to call this. A ketone differs because a ketone has an alkyl group attached to the carbonyl, like a CH3, a CH2, CH3. So let's look at the family of carbonyl compounds. Here are the first three members of this carbonyl family. This isn't a particular order, but this is the order we want to teach in. This is your aldehyde. Okay, I'm going to circle in, this is in red anyway, carbonyl. What's different? Aldehyde has a hydrogen attached to the carbon. The ketone, this is the ketone, has an alkyl group attached, and the carboxylic acid has a OH attached. So hopefully you can clearly see the difference there. Now let's look at the next 3 or 4 members. Let's start with an ester, because some of you will have come across an ester in GCSE. Here's your carbonyl. What do you notice? O and an alkyl group. So again, please look at the 4 molecules so far. Next one, let's go to a family of compounds called acyl chlorides, and what's different here is your chlorine. If I was to compare an aldehyde at the top here with a acyl chloride, then the Cl and the H are your differentiators. The acid and hydrides we will look at later on, and in the case of amides, and the biologists should be familiar with this when you've studied amino acids and peptide links, the difference here is NH2. So you can see clearly 1, 2, 3, 4, 5, 6, 7 members of the carbonyl family. They're all different as to what is attached to the carbonyl carbon. So that's the first thing to know. Secondly, carbonyl compounds in the case of aldehydes and ketones. So let's now focus on aldehydes and ketones. You have a really polar carbonyl group. Carbon is delta plus. Oxygen is the second most electronegative element in the periodic table. It's very much electronegative, so electrons get pushed towards this carbon. Okay, in terms of quickly physical properties, they have higher boiling points than alkanes of corresponding MR or similar MR due to hydrogen bonding. And please remember, with all organics that are soluble in water, their solubility will decrease as the size of the carbon chain length increases, because of van der Waals forces are getting bigger. So here is a comparison of the structural formula for an aldehyde, for a ketone. Both of these have the same MR. This is an aldehyde, skeletal formula, and you've got the skeletal formula for the ketone. Okay, I don't want to spend too long on nomenclature because the rules have been studied in year 12 before. Just to, excuse me, how to name. Just want you to focus on 3-methyl butanol, and why is it 3-methyl butanol? The carbonyl carbon is your first carbon. It takes precedence. Carbon 2, carbon 3. Methyl is on carbon 3, so 3-methyl butanol. Notice about ketones. That's your propanone. This is hexanthreone. Carbon 1, carbon 2, carbon 3. Now, it can't be 1, 2, 3, 4 because the rule is shortest number carbon atom. So the functional group is on carbon 3, hexanthreone. You can have hexanthreone if you want to move this there. So it becomes a positional isomer. Okay, what I want to move on to, and like I said, naming of these, you can work through this yourself using a decent textbook on how to name these. Okay, just to focus on recap of infrared spectrum, you have a distinctive peak for the carbonyl bond or carbonyl group in this region of 1680 to 1750 per centimeters. Okay, how do you test for how do you test for aldehydes and ketones? Okay, there are three main tests. To differentiate between an aldehyde and a ketone, you can use acidified potassium dichromate, where the orange mixture will change to green because the aldehyde is oxidized to a carboxylic acid and ketone will not react. The second or the most common reaction we use is this thing called Tollens reagent, ammoniacal silver nitrate. Here the reaction is when you mix this with an aldehyde and leave it in a water bath at a temperature of about 70 degrees, a silver mirror will form with the aldehyde. No change will happen with the ketone. And the third test is this one, which is with failing solution. Failing solution is blue, as you notice here. When you add an aldehyde to this, you will see a brick red precipitate with an aldehyde and nothing with a ketone. On the slide here, you can pause the video here and you can read about the tests. Again, I'm not spending too long on the tests. What you do need to know is the reason we're getting these positive tests for aldehydes is because aldehydes can be oxidized to carboxylic acids, whereas ketones can't be oxidized any further. And I'm hopeful that you have studied about oxidation of alcohols and aldehydes in year 12. Okay, so here is an example. Primary alcohol is oxidized to an aldehyde using acidified potassium dichromate, and an important condition, heat and distill. And a further distillation oxidation can occur where the aldehyde can be oxidized to a carboxylic acid. Carboxylic acids can be reduced to a aldehyde. Ketones are only oxidized to a secondary alcohol and that's it. Okay, now let's look at the nucleophilic addition reactions, and here I want to look at two mechanisms. The first mechanism is the following, where the reagent is NaBH4. You are going to use this as water as your solvent. The reaction is nucleophilic addition, or the mechanism is nucleophilic addition. It's a reduction reaction. There's only one product. Your nucleophile is a hydride ion. Let's look at the nucleophile. Let's look at the mechanism because that's what I want to focus on, the mechanism. So please note here, this is step 1 of the mechanism. The aldehyde, carbon is delta plus, oxygen is delta minus. Please note an arrow goes from the middle of the bond between carbon and oxygen towards the oxygen. This is a double-headed arrow that leaves carbon delta plus. Hydride has a pair of electrons, a lone pair, and it attacks the carbon. Look at these arrows carefully. That forms an intermediate where the hydrogen is added across the carbon. Oxygen has gained a pair of electrons and it's negatively charged there. This is my intermediate stage. This is Mark 3. In Mark 4, oxygen has a lone pair on it. It attracts hydrogen plus. This hydrogen plus is the proton that is coming from water, and we form one product where an alcohol is formed, and this is a reduction reaction. Same reaction will take place with a ketone, and um, and you can get an optical isomer formed here depending on the aldehyde or the ketone you're going to use. Okay, the next one is the reaction with the cyanide ions. And in the case of a cyanide ion, we're going to use potassium cyanide and HCl, because HCN on its own is very corrosive, flammable, unstable. The nucleophile is a cyanide ion. And here again, please note, the cyanide ion attacks the carbon. Step 1. There's a movement of a pair of electrons to oxygen, because oxygen is more electronegative. So exactly same as the previous mechanism. The intermediate is exactly the same. The cyanide is added across the carbon. CH3 and H stay where they are, and then the oxygen has a lone pair. You don't have to show these two lone pairs. Then it attacks the hydrogen. This H plus is coming from HCl now, and it forms a optical or a compound that's chiral. It has 4 different groups attached, and the name of this compound is, if it is going to be 1,2-hydroxypropane nitrile. 2-hydroxypropane nitrile. Now, why is this reaction very important? On the next slide, you will realize why it's more important. The compound, the chiral compound that is produced here, has a mirror image. But the two enantiomers in this mirror images cancel the plane of polarized light, because we have a racemic mixture where the two isomers occur in equal proportions. And the reason why you need to know, and it's an extremely important reason, and that is because the aldehyde or the ketone here has a carbonyl compound which is very planar. So the planar carbonyl is attacked by cyanide ions from above, look, from above or from below the plane of the carbon equally. The word equally, that's why I've highlighted it in red here, which results in a mixture of isomers in equal proportions. So please read this again. The carbonyl is planar. The cyanide ion, the nucleophile, attacks the carbonyl group from above or below the plane equally, resulting in a racemic mixture. And the last thing on here, and before I go into the last thing, HCN is toxic and flammable, and we're using KCN with HCl instead. The last thing we're looking at is the following: the synthesis of 2-hydroxypropanoic acid, better known as lactic acid. We're looking at how lactic acid is made in a 2-step process from ethanol. Number 1, nucleophilic addition reaction of ethanol with HCN or with KCN HCl forms 2-hydroxypropane nitrile. That then undergoes electrolysis with HCl and water to form, please note here now, the cyanide ion has been hydrolyzed to form the carboxylic ion, the carboxylic group. The molecule formed here is optically inactive, and the two isomers or the enantiomers are present in a racemic mixture because it is being made from 2-hydroxypropane nitrile, as it is made from ethanol. So in the whole process, we're producing optically inactive compounds here. So this is why lactic acid made in this process is optically inactive. And you can have a read of this slide. Pause your video here to read this slide to give you more information of what is going on. And then the next slide, I'll just put that on as well. Just another way of illustrating what is going on. Hopefully it's a bit clearer for you. And that's basically the end of this video on a very quick overview of aldehydes and ketones.